Hello everyone. Today we are going to learn how to use the Abaqus to analyze 1D direct to analyze structure under 1D loading using the direct stiffness method. So this is the problem statement. A structure like this is made of aluminum. The Young's modulus for aluminum is 10 megapsi, and the Poisson's ratio is 0.3. The geometry is showing here. The thickness for the plate is 1 inches, and the length for the entire plate is 16 by 10. And while there are two hollows in the middle, each of them has a length of 12 inches and 2 inches in height. The left-hand side is pinned, while your right-hand side has some loading. For this model, we are going to use unit loading, which means 1 pound for this structure. Recall the direct stiffness method. We can represent this geometry by a bunch of springs and nodes in either series or in parallel. The stiffness for the spring is K equals to E times A divided by L, where E is the Young's modulus for your material, A is the cross-section area, and L is the length for your member. And this 3 rectangular member, we can represent that by 3 springs, while the last one, this one, we can represent it by another spring. If you following this calculations, you will have the stiffness calculated here. K1 equals to 1.67 e to the power of 6 pounds per inches, while K2 equals to 25 E6 pounds per inches. Now let's see how do we use Abaqus, create Abaqus input file for that. Create a text document first. Call it input. I already have this here, but let me rewrite it from the very beginning. So your first step is to define the node. For the stiffness, we have one node. This is the second node. This is the third node. So double star means this is just a comment. It won't run in your program. So we define node with the first node coordinate, let's say 0, 0. The second node, the coordinate, since the information for the length is already buried inside the spring, so we don't actually need to care too much about this length. So we just simply name it 1, 0. And the third node, let's say 2, 0. After defining the nodes coordinate, now we define the spring constant. So spring 1, the element set, we create a set for that called S1, means spring 1. This is the name of the spring. And then this is 1D and 1 definitions. And this one, we have the spring constant written here, 1.67 E6. So we can do 1.6. Actually, let's do more accurate. So type more 6 here, and then 7 E6. And then we define spring 2. Element sets as 2. Again, 1, 1. And then the spring constant for the second one is 25 E6. After having all the elements, now we need to connect them together by defining the element connectivity. So the first element, all the elements should be a type of spring 2, which is 2-node spring. And then let's call the element set S1. So for the first 3 spring, they have the same quantity or same properties. So the first member, let's call, should be connecting the first node and the second node. This is the sequence of the element or the sequence of the spring. This is the start node. This is the ending node. So second one also connecting 1 to 2. The third one also connecting 1 and 2, which means this 3 spring is in parallel, connecting the node 1 and the node 2. And then the fourth one should have the properties of S2. So it should be a 2-node spring and it should have the property of S2. And the fourth one should be connecting node 2 and node 3. Now we can start our step. And it should be a static step. This is with 1 increment and total time is 1. For static, this doesn't matter. And then we should define the boundary condition. Let's write a note here. Define. This is just a comment. You can, if you want, you can get rid of that. So boundary, and our boundary is at 1 and it's pinged. So we say 1 pinged. After defining the boundary, now we can apply the loading. The loading should be on the right-hand side, and it's a concentrated load. Concentrated load is, the command for concentrated load is cload. And then it applied at node 3 with the dimension of 1 because it's 1D. And the magnitude, notice that here we should put -1 for the magnitude because it's tension. And then finally, we point out the output. For this case, we do a field output. Field output means the output for all the elements and the node. And we require the element output, because we care most about the element. And for spring element, this 2 mainly means E means strain and S means stress. But for the spring, E means the deformation inside the spring, and S means the internal force inside the spring. And finally, we end this step. So now you can save it as an INP file. Just change the extension, or let's just save it. And then in your folder, change the extension to INP file. Now we can use Abaqus to run it. Open Abaqus. So the most important thing is to set the working directory to the folder you want. Now, in the job, we can create a job. Call it manual input. Sorry. And here, the source for the input file, instead of from the model, we select the input file. Select the input file we just created. Now we can do the data check first. Make sure that there's nothing wrong with it. The warnings, and if you have any problem with your input file, it will show it in your message and warnings and arrows. They check complete and there's no warnings or arrows, so we can submit. While waiting, we can start. Oh, it's already done. It only has one step. So when you have something here, it's already done. And the status is completed. Now we can check the results. This is the 3 spring was combined into one big spring here. So now if you see the stress and displacements, well, the stress means the internal force, while the strain means the displacement for the spring. We can prop the value here using the query and then select the elements. And now select the E11 here, which means the X horizontal displacement. For member 1, you can see that is 2e minus 7. For member 2, it's also 2e minus 7. For member 3, it's also 2e minus 7. That means this 3 spring has the same deformation, which is 2e minus 7. This node is moving to the right by 2e minus 7. And then for spring 4, you can see it's 4e minus 8, which means this node only moved by 4e minus 8. That's how this model is shown. Now we can do in another way. Instead of creating the input file ourselves, we create a new job, create a new model for here. So to create a model in Abaqus for this case, the only object we need is 3 reference points here, here, and here, representing these 3 points. And there's no mass included. So we can create just create a reference point. So select the discrete region, use the 2D, and then select the point. Call it reference point. And just make it at 0. So now you have a reference point. The material, we don't need material properties here since all the material property will be given in the spring section. Now let's, in the assembly, we create assembly. And assembly is the one that is used for analyze. So we apply assembly. Now you have this point. And we can patterning, use this tool in the assembly. We can pattern the reference points. Vertically, we don't need any of that, so just type 1. Horizontally, we need 3 of that. And the offset, let's just leave it 1. Because as I said, the coordinate for this 3 point is not important since the geometry is included inside the spring. So once you have this finished, remember to save the file. Let's call it model 2D. Now we can create the spring. So under the assembly and engineering features, you have the spring dashboard. And connecting 2 points, call it spring 1 or S1. We select the first point and the second point. So you have this window here. And the spring stiffness, as we mentioned, it should be 1.67 E6. 1.67, we can type more 6 here, 6. And we don't have dashed pot here. And remember that we have actually 3 spring combining this 2. So we can add the second pair and also add the third pair to it. So in total, we have 3 pairs sharing the same spring stiffness. Create another one, call it S2. From the second point to the third point. And the spring stiffness is 25 E6. Now we can create a step. Step, let's call it C loading, concentrated loading, static, and leave everything default. In the field output, this field output. So the only thing we need is the stress S and the strain E. And for spring, it means internal force and the strain. And now we don't need any history output, so we can delete this one. Now in the loading, we can create a boundary condition. First, we create a pin boundary condition here. Even before our loading, the boundary condition already exists. So we select the initial say ping here, and then choose the point we want and choose pinged. And now we create our concentrated loading. So the load must be inside this loading step. Call it C load. Concentrated force. Select this point, which is the point we applied load. And as at horizontally, it has a magnitude of 1. Vertically is 0. You can see that load is applied here, boundary condition is applied here. Now we can do the job. Model input. So this is input from model 1, which is the model we just created. We don't need any history output, so let's see. If nothing goes wrong, this should have exactly the same solution as the previous one. It's finished. It's very fast since we only have 3 nodes here. And you can see that they're exactly the same. If you prop the value in the element, the first one, let's see the string, let's see the displacement for the first element. I think the model is not, the output, history output is not correct. The output is here. Let's include the history output and see. It's done. So we can see E11 here. And if you query elements 1, I think something wrong. Oh, it's in the assembly, sorry. You need to choose here, select the assembly, because assembly is where to apply all the, like the node is. And you can see that the displacement here is 2e minus 7. And it's the same for all the element 1, 2, and 3. But when you see element 4, which represent this one, the displacement is 4e minus 8. It's way smaller than this one, since the stiffness of the spring is way larger than this one. That is how you have for the, how you apply the stiffness, direct stiffness method to do the analysis of this problem. Now what we want to do is we try to do a real 3D model and see whether it is somewhat close to the simplified model. So now now go back to Abaqus, create a new file, and save call it model 3D. Now we do a 3D model. Solid, deformable, and approximate size is about 16. So let's put double the size, so 35 here. Now we use this line towards to create a line. Let's assume the coordinate here is 0. So the first point is 0, 0. The second point should be 0, 2. This is 0, 0. This is 0, 2. And this will be 12, 2. So the third one is 12, 2. And then 12, 4, 0, 4, 0, 6, 12, 6, 12, 8, 0, 8, 0, 10. And then this one will be 16, 10. And then 16, 0, 0, 0. You have this shape. Once it's done, the depth should be 1 inches. This should be your geometry. And then let's define a property. You should follow this step. So in the property, because this is made of aluminum, which has choose the elastic, which has a Young's modulus of 10 MSI, Poisson's ratio 0.3. Now create assembly for analysis using dependence. This will be your assembly. And then in the step, create a C loading. Static general, everything keeps the same. You don't need to change anything to it. Here, now we can output the displacement and the stress. And then interaction, we don't need interaction here. We directly went to loading. First, create a boundary condition in the initial. Initial means before the analysis. Boundary condition. So choose everything on the left-hand side, holding Shift and select all the surface. Choose pinned here. And then for the loading, to make it more uniform, instead of concentrated loading, now we select a pressure here. And or surface traction is the same. So select this surface, apply the traction. Remember that before we apply the concentrated load, 1 pumps. So now if you apply the pressure on the right hand side, it should be 1 pumps divided by the cross-section area, which is 10 inches square. So it should be 0.1. And this should be pointing outside, should be a tension. So the magnitude should be minus. If you see your arrow is pointing to the right, is the correct way. And then go to mesh. First, we define the element type before we define the element type, let's do element control first. Use tetrahedral here. And so now all the element will be simulated by tetrahedral. And now select the element type. Make sure that this should be a C3D10 10 node quadratic, or let's do linear here. C3D4 node. This kind of elements is very good for tension compression, very efficient for that, but it's not very good for bending. So the stiffness may be a little bit larger. Now we do the mesh. So to do the mesh, first you need to create seed. And the thickness direction is 1 inches. So we want at least 2 nodes in the thickness direction. Let's do 0.5 here. This is already pretty coarse. And then you click this one to create a mesh. It's like this. It's already pretty coarse, and so the result may be a little bit off, and let's see whether it's good or not. Finally, create a job, call it model 3D, create from the model, and we can submit. Oh, sorry, I forgot to do this one. Property. When I have the property, you need to create a section. Call it aluminum section. And it should be solid homogeneous. And now you assign the section to the entire geometry. When it becomes green, it means the material property is assigned to the geometry. Now go back, submit this work. It went through the data check. Now it's trying to calculate. You can see that a 3D element, although it's already pretty coarse, it still takes a while to finish the calculation. The final geometry is like this. Let's see U1. You can see that it has a 3D distribution and a little bit bending here because of the boundary conditions. And we only care like what's the displacements here. So we can do probe. We can do probe values. Select node here. We will see anything on this edge. So instead of deform the shape, we choose the undeformed shape. So it's easier to see the node. And let's see something on the side first. You see the displacement is 2.2 e minus 7. If you still remember before we do the direct stiffness method is 2e minus 7. This is pretty close. The arrow is like 10%. And if you make it finer, it should be even better. And well, if you select this point, it's 2.1, it's even closer. So it has a spatially distribution along this edge. And along this edge, which is the node 3, this is 2.58. And this is the 2.58 and this is 2.1. So the difference is about 4.6 e minus 8. If you still remember, the displacement for this part should be 4 e minus 8. So the arrow is like around 15%, 20% something. And it's also different from top and bottom. The bottom is like 2.29 minus 1.8. So it's around 3.9 e minus 7. So this on the top and bottom is smaller than the value we had using the direct stiffness method, while the one in the middle is larger. So, but it's not offset a lot. And if you make the mesh finer, I think it should be even closer. So in conclusion, the direct stiffness method can well represent the model, but it cannot show the full details. For example, about the stress concentration, like at which location it has the maximum stress. So this is how you use Abaqus to do a 1D direct stiffness method simulation. Hope that you can learn something from this video. Thanks for watching.